Hi, here's another problem using Newton's second law, and in this case we're going to see sometimes it's convenient to rotate our coordinate system to align as many vectors, force vectors, with the component axes as possible. So pause for a second and read this question. Alright, so part A and part B are two different scenarios. In part A, the crate is at rest on the ramp. Part B, it's given a slight push and begins to accelerate down the ramp. So let's look at part A. We're going to start as usual with our picture, and we're going to go ahead and draw the force vector. So I know for sure that I've got my non-contact force, gravitational force. We know that points straight down. And the only thing else that's touching the crate, we're ignoring air resistance, is the ramp. And so the ramp is a surface contact, which means there's two possible forces we could have. We have one, which is the normal force, Fn, which is perpendicular to the ramp surface, and we have a second one, which is the frictional force. In this case, part A, it's not moving. It's not sliding, I should say. The object is not sliding along the surface, therefore it's static frictional force. And that's the only things touching our object, so that is it. And we're going to go ahead and draw a free body diagram with those forces. Alright, so I've gone ahead and redrawn the vectors at a common point in the free body diagram, and I've also traced out the ramp angle just so we can see that. Now, one important thing to note here is that it says determine the smallest value of the coefficient of static friction so that the crate does not slip. That means we're at the point of slipping. That means we're actually at the max static friction. Because if it had a smaller value, it could not be slipping and not be at the max, but you know, we're about to slip. We're at the maximum value of the static friction, which is good to know because there's a formula for the magnitude there. Now we'll look at your free body diagram. We're always free to choose how we draw the coordinate axes. Well, we're going to go ahead and try to do this in a way that aligns as many of the force vectors parallel to one or the other component axis. So I'm going to make the y-axis go like this, and I'm going to go ahead and make the x-axis go down like this, okay? So you're always free to choose your axes. Once you've chosen them, you just stick with them. Now we've got two forces, the static frictional force and the normal force, that are already aligned with the axes, and it's only the gravitational force where we have to do some trigonometry. Now to figure out the angle, we know that this angle here, this is 30 degrees, right? That means that this angle is 60. And that means that this angle is 30 as well, right? So that helps us figure some stuff out. And we're going to calculate the components of FG here in this way. So notice that FG, we've got a FGX, and we've got here an FGY. And so let's go ahead and make our table and figure out all the components that we have for these vectors. All right, first off, we'll note that because this is a static equilibrium here, we're not moving here, that acceleration is 0. And therefore, we've got a 0 and a 0 here. Now for the forces, we can see the simple ones to do are the normal force, which is only along the y-axis, so we got a 0 here. And all of the magnitude, Fn, we can see it points in the positive y direction for the normal force. For the static frictional force, nothing is along our y-coordinate, so that's 0. And so plus is down the ramp for x. So that means that the static frictional force, its entire magnitude, Fs max, it's going to be directed in the negative x direction. For the gravitational force, we're going to have to actually do a little bit of trigonometry here. We've got a right triangle there, and we're going to go ahead and write down the components x and y for the gravitational force by looking at our picture in the free body diagram, and we'll use the 30-degree angle. So look at the quadrant here. X is positive here, y is negative, right? So we're going to have a positive x value and a negative y value, and then we're going to write the magnitude. I'm just going to write this as mg because we know that's the formula for the magnitude of the gravitational force. And finally, now look at the let's do the x component. Here it is. That is opposite of 30, so we're going to choose sine. And the y component, of course, is adjacent to 30, so we'll choose cosine of 30 degrees. And now we've got those values here. So we got a x component of plus mg sine 30 degrees and minus mg cosine 30 degrees. And so by reorienting our coordinates, we only had to do trigonometry with one of the vectors, which makes our work a lot easier. From here on out, we're going to go ahead and use Newton's second law and put the information in our data table into that equation for the x and y directions. So we do know a few things here, right? We do know what the value of m is. We know what the value of g, of course, is. It turns out that if we look up the magnitude, let's look at the static frictional force. If it's at its maximum, there's a formula. It's the static coefficient friction mu s times the normal force. So we can actually put that into our data table as well. So this is actually going to be equal to, the minus sign still there, mu s times Fn. And let's go ahead and feed that into Newton's second law. All right, so let's go ahead and plug in our numbers here. So for the x column, it looks like A is 0. And when we add up the forces, we're going to get a positive mg sine 30 degrees plus a 0 for the normal x. And then for the static frictional force, it's going to be a negative mu s times Fn. And for the y direction, let's input our data from the table of a 0 for the acceleration. And we're going to add up all the forces. We've got a minus mg cosine 30 degrees, and then we have a positive Fn. And so we've got our two equations. Recall what we're trying to solve for. We're trying to solve for mu sub s. We know m, we know g. We don't know Fn either, but we've got two equations, two unknowns, we can solve for it. So let's go ahead and solve for Fn here. We're going to add the mg cosine theta to both sides. There we go, good. And we're going to go ahead and plug that into the other equation, and then we'll be able to solve for mu sub s, right? So in this case, if I add the mu s Fn to both sides, that's equal to mg sine 30 degrees, and I can go ahead and divide by Fn, and we're going to get this equation here. And finally, we're going to go ahead and input the value of Fn right into that equation from here. And let's go ahead and write that all out. So I've substituted in Fn, and hey, look, looks like the mass times gravity cancels out. So a lot of times, actually, gravitational force, when it's involved in a problem, the mass will actually cancel out. And if we use a little trigonometry identity, sine 30 divided by cosine 30 is equal to tangent 30. And if you put that into your calculator, you're going to get a coefficient of static friction about 0.58. Remember, it's dimensionless. That is your answer for part A. Now for part B, things are going to change a little bit here, because now we've given this thing a nudge enough to where it starts to slide, and it's going to be sliding down the ramp. So there's a lot of things we could still use. Let's copy and take some stuff down and look at part B. So a few things to change in part B. We know that the acceleration is not going to be 0 anymore, but we do know that it's going to be pointed downwards. It's going to be sliding down the ramp. Now we know that when you're sliding along a surface, we no longer call it static friction, we call it kinetic friction. So we're going to have to change this to kinetic friction. And also kinetic friction has a slightly smaller value there of the coefficient. So we're going to go ahead and make that a little bit tinier vector there. So there's our new vector for the kinetic friction there. So let's make those changes to our table as well. Right, so now we can, so the gravitational force hasn't changed. That is still the same there, so we're good with that. The normal force, we still don't know what it is, but we can write it like that. And we're going to need to change the static frictional force into a kinetic frictional force. So let's go ahead and look at our picture again here. So the kinetic frictional force here, it's going to, slightly different number there, call it F sub k, and we can see that again it's going to be in the negative x direction, 0 in the y direction, and we have a formula for that. If we go look that up, turns out the magnitude is mu k times Fn, so we'll go ahead and put that in there. All the magnitude in the negative x direction. Let me go write that correctly. Mu k times Fn. And now for the acceleration, well, it's parallel to the ramp surface. It's only along the x direction, so y is 0. We don't know what ax is, but we'll solve for it. Again, it's time to plug this all into Newton's second law, so I'll kind of do this quickly. Here's Newton's second law in the x direction, so we've got m ax is equal to mg sine 30 degrees minus mu k Fn. All right, and we can also look at the other direction here. So m ay, sum up the y components. So we got an a is 0 here. We got 0 is equal to minus mg cosine 30 degrees plus Fn, and that lets us solve for Fn. Fn is going to be equal to mg cosine 30 degrees. And that kind of tells us that the normal force here, it's balanced by the y component, right, of the gravitational force, so that the object isn't, you know, flying off the ramp or crashing through it. And now we're just going to go ahead and plug this in here, and we'll solve for A. So we plugged in Fn. All we need to do now is divide by the mass, and we're going to end up with the acceleration, and we'll go ahead and plug our numbers in there. So I looked, the mass is 3 kilograms, the coefficient of kinetic friction 0.45, put in all our numbers, enter into the calculator, and we get a value of about 1.08 meters per second squared. And if we want to get the magnitude of that acceleration, of course, we know ay is 0, so the magnitude of the acceleration is just going to be the absolute value of the other component, the non-zero component. And so we end up with the answer here. There we go. So I just want to point out here how we're always going to get different equations after we apply Newton's second law and the analysis. So, you know, it's the methodology that you use, the picture, draw your forces, free body diagram, use your table, figure out the x and y components, apply Newton's second law in the x and y direction. If you follow those steps, you'll always end up with the right formula, but there's no way to predict what it will be in advance. So learn the procedure, learn the steps, and you're going to do great on this stuff.